Welcome, my friends! In this video, we will discuss how to calculate a one-sample mean confidence interval using the z-distribution. Let's begin by discussing the three assumptions required in order to calculate this type of confidence interval. We must have a simple random sample, the value of the population standard deviation sigma must be known, and if the distribution of data is normal, any sample size will work, otherwise the sample size n should be at least 30. Now let me make a few comments about these assumptions. In my experience, the first assumption is often implied, and you should assume that any confidence intervals that I compute come from data gathered by use of a simple random sample, even if I don't explicitly state it. The assumption about knowing the population standard deviation is extraordinarily unrealistic. In order to calculate the population standard deviation, you need to know the population mean. But remember, the whole point of this test is to estimate the mean because we don't know it. If we don't know the mean, how could we possibly know the standard deviation? It's like saying that I visited the Statue of Liberty, but I've never been to America. No, you haven't, Harry! That's impossible! Okay, where were we? Ah, yes, the assumptions. Since we are in the classroom and not in the real world, many textbook problems miraculously provide you with the population standard deviation, the thing that's impossible to have. In that case, go forward with the confidence interval, and everything should be just great. The third assumption ensures that the distribution of x bar will be normal, either through having a normal initial distribution or through the central limit theorem if the sample size is at least 30. Okay, now that we have the assumptions out of the way, let's look to the formula for a one-sample confidence interval for the mean mu using the z-distribution. The formula is x bar plus or minus z times sigma divided by the square root of n, where mu is the population mean, x bar is the sample mean, z is the positive z-score associated with the desired level of confidence, sigma is the population standard deviation that we miraculously know, and n is the sample size. X bar is our point estimate for the mean, and this part is the margin of error. Notice something about the margin of error. Recall that sigma over the square root of n is just the standard deviation of the sampling distribution x bar. Also recall that a z-score represents the number of standard deviations an observation is from the mean. Therefore, the margin of error is just z standard deviations from x bar. Amazing! The specific z-score that we need will depend on our level of confidence, such as 90%, 95%, 99%, etc. The best way to show you how this all works is just to look at an example, so that's what we'll do now. Suppose a random sample of 49 college graduates found the mean yearly income to be $50,000. Assume the population standard deviation is known to be $7,000. Find a 95% confidence interval for the mean yearly income of college graduates. The first thing to do is to check our assumptions. Do we have a simple random sample? Yes, we do. Do we know the population standard deviation? Yes, indeed we do. Is the population normal, or is the sample size at least 30? Yes, we have a sample size of 49. We have met all three assumptions, so we can move forward with the confidence interval. Here is the formula for the one-sample z interval for the population mean. X bar is the sample mean of 50,000, sigma is the population standard deviation of 7,000, n is the sample size of 49, and the confidence level is 95%. The only number that we are missing is the z-score, which is the positive z-score corresponding to the 95% confidence level. If we draw the picture of this distribution, 95% of the probability falls between the upper and lower bounds. This also leaves 5% of the probability to be split between the two tails, 2.5% each. In decimal form, that's 0.95 and 0.025. X bar is our point estimate, which goes in the middle, which is 50,000, and the lower and upper bounds of the confidence interval will go at the cutoff points of the shaded area of the distribution. The z-score we need for the formula is the positive z-score corresponding to the upper bound. To find the z-score using the TI-84 calculator, we need to know the area to the left of our z-score. The area to the left of the z-score is these two areas added together, 0.025 plus 0.95, which is 0.975. Now we are ready to go to the calculator. In the calculator, press second, distribution, which is over the vars key, and then select option 3, which is inverse norm. Put in the area to the left, which in our case is 0.975, and leave mu and sigma at 0 and 1 for the standard normal distribution. Scroll down and paste. For older calculators without the previous menu, match this output that you see here. 0.975, 0, 1. When we press enter, we get 1.96 if we round to 2 decimal places, which is our z-score. Now that we have the z-score, we have everything we need to plug into the formula. We take 50,000 plus or minus 1.96 times 7,000 divided by the square root of 49. This becomes 50,000 plus 1.96 times 7,000 divided by the square root of 49, which is 51,960, and 50,000 minus 1.96 times 7,000 divided by the square root of 49, which is 48,040. These are the lower and upper boundaries on the graph. Our conclusion is that we are 95% confident that the interval between $48,040 and $51,960 contains the population mean income for college graduates. And we are done. One final note before I leave you. You probably noticed that the hardest part of this whole process was finding the z-score. Since the z-score depends on the confidence level, I have listed here some of the common z-scores, which might save you some time when completing problems in the future. So you're welcome. Alright my friends, we have finished our discussion of one sample z intervals. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.